Hello YouTube. Today we're going to measure the elastic properties and internal friction of a rectangular sample using the RFDA basic system. So what we're going to do is we're going to use this small hammer to tap the sample, and we're going to record a vibration signal using this microphone. We will send the vibration signal to the computer, where we will analyze the vibration signal and calculate the elastic properties. So the first thing we do is we start up the RFDA software. We will choose measurement, and we will give in the weight and dimensions of the sample. So from this sample, it's 148.48. Length is 18 millimeters. Weight is 34.99. And thickness is 8.93 millimeters. In the screen we also see the node distance. That's the distance between the two support wires. And it's important that the sample is supported in this way, because this way it's supported in the vibration nodes of the flexural vibration, which we are going to measure. Okay, now we just press measure and we tap the sample. So in these two screens, we see in the first screen we see the vibration signal that we recorded using the microphone. In the second screen we see the frequency spectrum with one large peak at around 7,900 Hz. This is the flexural vibration, and we see the internal friction. So now we tell the software that we measure the flexural vibration and we select the correct vibration. Now the software calculates the Young's modulus and the error that was calculated on the Young's modulus. So we also want to measure the shear modulus and the Poisson ratio. Therefore we need to induce the torsion vibration mode. And to be able to do that we have to change the setup a little bit. So now we support the sample on two fish wires this way, and what we're going to do to measure the torsion vibration mode is support the sample in a cross like this. So let's change the setup a little bit. We support the sample in a cross. We position the microphone in one of the corners, and we're going to tap the sample in the opposite corner. So let's do that. Now again we see the vibration signal that we recorded. The frequency spectrum is a little bit different. We see two peaks this time. The first peak is again around 7,900 Hz. That's the flexural frequency. And we see another big peak at around 10,000 Hz. That's the torsion frequency. Now to calculate the shear modulus and Poisson ratio, we have to say that we measure in flexural and torsion. We select the correct torsion frequency, and the software calculates the Young's modulus, shear modulus, and Poisson ratio. So the RFDA basic system is a very efficient and fast way to measure the elastic properties of samples. Now let's have a look at the reproducibility of the measurement results. So we're going to do a couple of measurements and see how the Young's modulus, shear modulus, and Poisson ratio change. So let's do another measurement. We see again that we have about the same Young's modulus, shear modulus, and Poisson ratio. Between measurements you will have a maximum difference between for the elastic properties of about 1%. So let's do some other measurements. Again, we have about the same results. Again, let's do it one more last time. Again, we see about the same results. So we have very good reproducibility for the elastic properties using this setup. Now let's have a look at some other samples which we can measure. This is another rectangle bar. It's a little bit smaller than the one we have measured. And the smallest we can measure is a rectangular bar like this with a length of about 2 centimeters. If we go any smaller, it's possible to measure smaller samples, but then it becomes physically very difficult to tap the sample and record the vibration signal. This is a cylindrical rod. It's also possible to measure with this setup. And disc-shaped sample. Now, let's look at some materials. What's important is that the material is stiff enough, so that when we tap the sample, you have a vibration signal. Basically, you have to hear some kind of ping that you can record. If we are going to tap, for example, a rubber type material which is not so stiff, we will not hear any ping, and it will be very difficult to measure this type of material. So very stiff materials, or stiff materials like this is fiber reinforced polymer. It's possible to measure this, or maybe some glass or ceramic material or metal. It's no problem to measure this. Another example is this aluminum foam, very porous material. Also possible to measure with this setup. And the big advantage we have over other techniques is when you tap this sample, we only apply very weak forces onto the sample. So you won't crush any of the porosities, and therefore you will also have a very good reproducibility of the elastic properties when you measure this type of material using the RDA basic system. Here's another example, very porous ceramic material. This is a diesel particle filter. Also very difficult to measure with other techniques, but we get very good results with the RDA basic system. Last example is this refractory brick, bigger sample. Measuring bigger samples is no problem. Maybe you have to use a little bit of a bigger hammer, but that's no problem. So measuring bigger samples is no problem. We can also measure this type of material at high temperature. So then we use the same type of setup. Of course, we're going to use different materials in our high temperature setup. And then we put the same setup inside of a furnace and perform measurements of the elastic properties and internal friction during heating and cooling. So normally we measure the elastic properties every 2 minutes during heating and cooling, and this way you can map out the elastic properties and internal friction of a material during heating and cooling. So for now, that was it. So I would like to thank you for your attention, and until next time.